Hello, in this video I am going to tell you about two-point boundary value problem. Boundary value problem arise in many engineering applications. A boundary value problem for a given differential equation consists of finding a solution of the given differential equation subject to given set of boundary conditions. We will also discuss eigenvalue problems, which is a special case of boundary value problem. Then we shall consider some simple boundary value problems and we'll see how we can solve them. After this video, there is a learning by doing activity in the form of a quiz which consists of 2 multiple choice questions. So after going through this video, go to quiz section for answering the questions based on it. These are the outlines of the contents in this video. First, we will go through the definition of two-point linear boundary value problem. Then we will see eigenvalue problems, which are a special case of boundary value problems. After that, we will see some examples of two-point boundary value problems and we will see how to get the solutions of these boundary value problems. Then there will be applications of boundary value problems to be seen here, and finally references on which the contents of this video are based will be given. A standard two-point linear boundary value problem is given by equation 1 along with the boundary conditions which involve the value of the dependent variable, which is y here, or its derivatives with respect to independent variable, which is x here. For two-point boundary value problems, the boundary condition should be specified at two different points, which generally are the end points of a geometry under consideration. There are mainly 3 types of boundary conditions, which are given here. The first type of boundary condition is called Dirichlet boundary condition, where value of the dependent variable y at two endpoints x is equal to a and x is equal to b are given. Gamma 1 and gamma 2 are two constants. Then there are boundary conditions of second type, which are called Newman boundary conditions, where value of the derivative of y with respect to x at the 2 points x is equal to a and x is equal to b are given. Here y prime denotes the derivative of y with respect to x. The third type of boundary conditions are mixed type, where value of y and its derivative at both these points are given in a mixed form. Here a0, a1, b0, b1 all are positive constants. Boundary value problems do not behave as nicely always, because there are boundary value problems for which the solution do not exist, and even if a solution exists, there might be many more solutions, which is a case of infinite solutions. Now let us see when a boundary value problem is called homogeneous and when it is called inhomogeneous. If Rx is equal to 0 in equation 1, the differential equation is homogeneous. Otherwise, it is inhomogeneous. Boundary conditions are homogeneous when gamma 1 and gamma 2 are 0, otherwise inhomogeneous. A boundary value problem is said to be homogeneous type if the differential equation as well as boundary conditions are homogeneous. Note that a homogeneous boundary value problem possesses only trivial solution, means the zero solution yx is equal to 0. This is a boundary value problem which has only trivial solution yx is equal to 0. This is the differential equation and these two are the boundary conditions. At x is equal to 0, y is equal to 0, and at x is equal to 1, y is equal to 0. As you can see here, The differential equation as well as both these boundary conditions are homogeneous. Now we will see how to find the solution of the boundary value problem, which is a homogeneous boundary value problem. The solution of the boundary value problem is given as yx is equal to c1 sin x plus c2 cos x, where c1 and c2 both are arbitrary constants to be determined with the help of boundary conditions which are given to us. Now the first boundary condition, y0 is equal to 0, implies c2 cos 0 is 0. This implies c2 is equal to 0. Therefore, solution can be given as yx is equal to c1 sin x. Now if we apply the second boundary condition, y of 1 is equal to 0, this implies c1 sin 1 is 0. Now this implies c1 is equal to 0 because sine of 1 cannot be 0. Therefore, both arbitrary constant c1 and c2 are 0. Therefore, the only solution is yx is equal to 0, which is a trivial solution of this homogeneous boundary value problem. Since in most of the practical applications we are interested in non-zero solutions of the system. To seek a non-zero solution of the homogeneous boundary value problems, we introduce a parameter lambda, which leads to eigenvalue problems, and so solution of such boundary value problems are called eigenfunctions. The parameter lambda is called eigenvalue. This is the eigenvalue problem. As you can see, here we have introduced a parameter lambda. This is the differential equation. These are the homogeneous boundary condition. The differential equation is also homogeneous. We will see that this eigenvalue problem has infinite number of solutions. Now we will see how to find the solution of this eigenvalue problem. The solution of this problem is given as yx is equal to c1 cos of lambda x plus c2 sine of lambda x. If we apply the first boundary condition, y0 is equal to 0, this implies c1 cos 0 is equal to 0. This implies c1 is equal to 0 because cos 0 is 1. Now if we apply the second boundary condition, that x is equal to L, y is equal to 0, this implies c1 cos of lambda L plus c2 sine of lambda L is 0. Now because c1 is 0, this part will be 0, so this will imply c2 sine of lambda L is 0. For non-trivial solution, non-trivial or non-zero solution, we require c2 to be non-zero. Therefore, sine of lambda L is 0. This can be written as equal to sine of n pi, where n is an integer. 0, 1, 2. This implies lambda L is equal to n pi. This gives you the value of lambda as n pi upon L, where n can take the value 0, 1, 2, etc. We do not want lambda to be 0, so we will take the values of n for eigenvalue problem as lambda is equal to n pi upon L, where n varies from 1, 2, 3 and so on. This lambda is called eigenvalue of the problem. So lambda is equal to n pi upon L, where n takes the value 1, 2, 3. Therefore, complete solution of this eigenvalue problem is given by this summation of all the possible solutions for different values of n. If we sum all the solution, this will be the final solution, this system of equation. This type of boundary value problems frequently occur in vibrations in dynamical systems. Let us see a very simple example of non-homogeneous system. This is a non-homogeneous system where Rx is equal to 1 here, and the boundary conditions are non-homogeneous. So both equation as well as boundary conditions both are non-homogeneous. Now we will see how we can find the solution of this simple non-homogeneous equation. So first we will find the solution of homogeneous equation. The solution of homogeneous equation, suppose we denote by YH, this is equal to C1 cos x plus C2 sin x. The particular integral yp x is equal to 1 upon d square plus 1 of 1, because Rx is equal to 1. This can be written as 1 upon 1 plus d square, and then we will apply binomial theorem to expand it. This is equal to 1 plus d square raised to the power minus 1 of 1. This is equal to 1 minus d square plus higher powers of d operating on 1, where d the operator is derivative with respect to x. So the value of this is equal to 1. So the particular integral for this equation is 1. Therefore, the general solution for this equation is sum of homogeneous part plus the particular integral yp, which is equal to C1 cos x plus C2 sin x plus 1. Now if we apply these two boundary conditions, y0 is equal to 1 and the other boundary condition, that y of pi by 2 is equal to 0, this will lead to the solution yx is equal to 1 minus sin x after determining the values of the constants C1 and C2. So this is the final solution of this non-homogeneous boundary value problem. Now we will see if we make a slight change in the boundary conditions and try to find out the solution of the same non-homogeneous differential equation, where we will take the boundary conditions as y at pi by 4 is equal to 2 and value of y at 5 pi by 4 is equal to 2. Then this gives C1 plus C2 is equal to square root of 2 and minus C1 minus C2 is also square of root of 2. Now we can see that both these equations are inconsistent. So in this case there will not be any solution. So for these boundary conditions there is no solution of boundary value problem. The same boundary value problem but only with changed boundary conditions. Whereas in the previous boundary conditions we had seen that this was a unique solution. So with the slight change in the boundary conditions we can see that boundary value problem behave differently. There can be a unique solution, there can be no solution at all, or there can be infinite number of solutions as we have seen in eigenvalue problems. Thus we have seen through these solutions that with small changes in boundary conditions the boundary value problem may or may not have solution. Here the solution of non-homogeneous boundary value problem which we considered earlier has been depicted graphically. This is the graph of the solution. This is the solution in the larger interval. As sin x is a periodic function, this shows that the periodic nature of the solution is maintained. These are some examples of boundary value problems with changed boundary conditions where boundary value problems behave differently in terms of solutions. As you can see, the differential equation in all these three cases is same. Only there is a small change in boundary conditions. With these boundary conditions, this problem has a unique solution. Whereas with these boundary conditions, this has no solution at all. However, with these boundary conditions, this boundary value problem has infinite number of solutions. These are some applications of boundary value problems where we can apply this theory of study of boundary value problems: steady state flow and potential problems, heat flow problems to find temperature distribution, vibrations, wave mechanics, gas dynamics. Here are some practical problems which lead to boundary value problems. This is the equation which is for a steady state heat balance for a rod. These are the boundary conditions. One can solve it very easily with the concepts which we have discussed here. This is diffusion equation. This also can be solved very easily. This is the equation for insulated heated rod with a uniform heat source. These are the boundary conditions. This is the basic differential equation for elastic curves. This is the differential equations. These are the corresponding boundary conditions which can be solved. These are the references on which the contents of this video are based. Thank you.